For the longest time, a practical working quantum computer has felt like something straight out of science fiction. But a really exciting breakthrough from IBM has just brought that dream a whole lot closer to reality. So today, we're going to crack open this huge leap forward. So, what's all the fuss about? Well, you've got to understand, quantum computing isn't just about making a faster version of the computer on your desk. We are talking about a totally new kind of computing, one with a kind of power that's almost impossible to wrap your head around. And to give you just a little taste of the scale we're talking about, think about this number, 300. That's it. If you could get just 300 fully entangled quantum bits, we call them qubits, working together, they could hold more information than there are atoms in the entire known universe. Yeah, that's not just a small step up, it's a complete game changer. And this kind of power isn't for loading websites faster. It's for solving problems that are literally impossible for even the biggest supercomputers we have today. I mean, think about it. Designing life-saving drugs by perfectly simulating how proteins fold, creating truly unbreakable codes, or even running a simulation of how our universe began. It's wild. So what's the secret sauce behind all this power? Well, let's meet the hero of our story, which also happens to be the biggest challenge, the qubit. This is the fundamental building block of any quantum computer. The real magic is in how different these are from what we're used to. A classical bit, right? The kind in your phone? It's basically a light switch. It's either on or off, a 1 or a 0. Simple. But a qubit, a qubit is like a spinning coin. It can be heads for 1, tails for 0, or, and this is the crazy part, it can exist in the state of spinning, representing both heads and tails at the exact same time. It's a quantum state called superposition, and that's where all that incredible power comes from. Okay, but here's the catch, and it's a really big one. That special spinning state is ridiculously delicate. I mean, the tiniest change in temperature, a single stray bit of radiation, and poof, that beautiful quantum state is gone. Qubits are, well, they're super finicky. In that fragility, that finickiness, it leads to errors. And in the quantum world, we don't just have one type of error to worry about. Oh no, we've got two very different villains that are constantly trying to mess up our calculations. All right, so the first villain is one we kind of already know. It's called a bit flip. It's pretty much what it sounds like, just like an error in a normal computer, where a bit that's supposed to be a 0 accidentally flips over to a 1. We actually have ways to handle this. But the second villain, now this is the really tough one. It's called a phase flip, and it's a problem that only exists in the quantum realm. It doesn't change the qubit from a 0 to a 1. Instead, it messes with a special connection, the entanglement, between multiple qubits. You can think of it like a musician in an orchestra suddenly playing out of sync. It throws the whole performance off. So this all leads to a really obvious question, right? If these qubits are making mistakes, why don't we just, peek in on them, see what's wrong, and fix the errors as they pop up? And here we are at the mind-bending paradox at the very heart of quantum computing. The moment you try to measure or even just observe a qubit to see if it has an error, it forces it to stop spinning. It collapses its special quantum state down to a boring old 0 or 1. You destroy the very information you were trying to save. It's the ultimate catch-22. And for years, this paradox was a massive wall. Scientists could build systems that were pretty good at correcting for bit flips, or they could build systems to correct for phase flips, but they could never, ever do both at the same time. You'd solve for one villain, and the other one would sneak in and wreck the whole thing. Until now. This is where it gets good. Researchers at IBM had one of those incredible scientific aha moments and found a really clever and honestly beautiful way around this problem. So to get what they did, you first need to picture the old way of doing things. Before this, pretty much every attempt at error correction laid the qubits out in a simple, one-dimensional line, kind of like beads on a string. So what was IBM's brilliant idea? Instead of a line, they arranged their qubits in a two-dimensional grid, a square. I know, it sounds almost too simple, right? But changing the layout, the geometry, that was the key to unlocking everything. So, how does this matrix actually work? Well, you've got two kinds of qubits in there. The data qubits are the ones actually holding the information for your calculation. But then you have these special syndrome qubits that are sprinkled into the grid to act as little detectives. Because they're in a grid, each qubit has more neighbors. And this lets the syndrome qubits check on their neighbors in a way that gives them clues about both bit flips and phase flips, all at the same time. And the best part? They do it without ever looking directly at the data qubits, so they never collapse that precious quantum state. It's like being able to tell if your neighbor's house is okay just by listening to the faint sounds through the wall. You get all the info you need without having to barge in. Okay, so this is a huge, huge step forward. It basically proves that this kind of simultaneous error correction is actually possible. But does that mean you can go out and buy a quantum computer tomorrow? Well, not quite. The journey is definitely not over yet. So what's still on the to-do list? Well, there are still some pretty major engineering hurdles. For one, scientists have to get much better at actually manufacturing these superconducting qubits so they have super low error rates right from the start. And then, of course, they need to scale this whole square chip design way, way up, from just a handful of qubits to hundreds, maybe even thousands. But let's be absolutely clear about this. A fundamental, show-stopping barrier has just been shattered. The problem that for so long seemed impossible, correcting for both types of quantum error at once, has now been solved. It shifts the whole conversation about quantum computing from a question of if to a question of when. And that leaves us with one last, really exciting thought. Once we finally have this unimaginable power, what's the first world-changing problem we're going to solve?